right, hopefully you guys can hear my voice okay. If not, just crank the volume on the smartboard. You guys all have the notes booklet that I handed out on Monday. If you don't have it because you weren't here on Monday, so that's Aaron, Devin, Miranda, Will, Wyatt, and Tyler Workman. There are extra copies of it sitting on the demo desk to the right of the smartboard. If you want to grab that, there's actually a little package that has the notes booklet, the assignment booklet, and the reading in it. The unit that we're doing now, as some of you might have known from the lab that we did yesterday, is periodic motions. We're going to look at things that have a regular, repetitive back and forth movement. And so we're going to start our look at that kind of periodic motion by looking at pendulums. And the first little bit here is just a whole bunch of definitions. So the first definition is oscillation. So oscillation is just the word we use for the repetition, right? It's a repetitive back and forth motion. So a lot of times it helps, especially with pendulums even, to think of a swing, because that is something that moves with periodic motion. It has an oscillation, a repetitive back and forth movement, and it also happens to be a pendulum. A cycle is one complete oscillation. So that's, for pendulums especially, that would be back and forth. And you guys found that out yesterday doing the pendulum line. So, you know, you have a pendulum that hangs down, and you let it swing, so that you can pull it up to some amplitude, you know, by some angle, and it's swinging all the way one way, and then all the way back again. That is one cycle. Oscillatory motion is repetitive, predictable motion that involves a back and forth movement where the period of each cycle is constant. So it always takes the same amount of time to move back and forth. And there are a lot of things naturally, like some things in nature, as well as things that are man-made, that move with oscillatory motion. Things like water waves, guitar strings, car pistons, and that's just to name a few. These all move with what's called oscillatory motion. Period is a term we've already talked about in terms of circular motion, but period is signified the variables capital T, and it is the time taken for one complete oscillation. It's measured in seconds, and frequency, which is a lowercase f, is the number of oscillations per second. So period and frequency have an inverse relationship. Period is the time that it takes for one oscillation. Frequency is the number of oscillations you can get per second, and the unit for frequency is hertz. And period and frequency are related by a very simple formula, and you had to use that formula yesterday as well. We've used it in circular motion. So period is 1 divided by frequency. That's what's on your formula sheet. You can also find frequency by doing 1 divided by period. That one is not on your formula sheet. So pendulum, as you guys learned yesterday, is basically just a mass that's attached to some sort of string. The mass is referred to as the pendulum bob. The mass hangs down, and it can be made to swing back and forth. So in terms of just doing a little diagrammatic representation of that, you have something that's hanging down from, in this case, we'll say that's maybe just the ceiling, or even the pendulum hangs down, and it has some length. So that's the length of the pendulum. And you can pull it up to some maximum distance away from what's called the equilibrium point. That hanging straight down is the equilibrium. And you can pull it some angle away from that equilibrium point, which is really, like most pendulums, although you can pull them up pretty high, they have sort of a maximum angle at which they'll still function as a pendulum, which means they'll still have a regular repetitive motion. And when it's pulled up to those heights, it has a maximum potential energy. So the potential energy is a maximum at those pulled back heights. At the equilibrium point, EK is a maximum. So what that basically means is at the pulled up points, there's no EK. And at the equilibrium position, there's no EP. And we're going to talk about like kind of what happens there a little bit at those points, the equilibrium point and then the maximum points. The period of vibration for a pendulum depends only on the length of the pendulum. It depends on the gravitational field strength, but for the most part we're always on Earth, although not always in the questions. But again, from the lab that you guys did yesterday, you should have found that, you know, once you had done your graph properly, when you had period versus mass, or period versus angle, then you should have basically gotten about a horizontal line for both of those. It's actually period versus length where you get a bit of a difference. And it's kind of like, it looked like a straight line, and so like it's okay to do a straight line. It's really, it's an inverse, like it's an inverse square relationship. Because in the formula for period of a pendulum is 2 times pi times the square root of length divided by acceleration due to gravity. It's a nice, easy formula to use when you're solving for period. When you're solving for length or gravitational field strength, it becomes a little bit more challenging. And then this formula is on your formula sheet. And that is on your formula sheet under the waves section, right at the very top of waves. So the top middle portion of your formula sheet. Okay. Remember, you guys can have graphical stop and start this, so you can stop and start this yourself. If I move the page up and down, or change pages before you're ready to go on. So we'll just do a few examples using that formula. We'll do one for solving for period, one for solving for length, and one for solving for gravitational field strength, just because it takes a little bit more algebra. So example 1, a swing is a type of pendulum. A swing in a playground has a length of 2.15 meters. Find the period of this swing. So we have a length, 2.15 meters. Although it doesn't say so, we're going to assume the playground is on Earth. So G is 9.81 meters per second squared. And we want to find period. So period is 2 pi times the square root of L over G. So 2 times pi times the square root of 2.15 meters divided by 9.81 meters per second squared. Please, please take the time to plug this into your calculator and make sure you can get it, because it does require a little bit of practice to know how to put everything in there. Basically, you can put it right in your calculator. Is 2 times pi times the square root of 2.15 divided by 9.81. And you should get 2.94 seconds. So again, that one's pretty straightforward. You guys catch up a little? Actually, while you're... Okay, so we want to now, for example, 2, find the length of a pendulum on Earth that has a period of 0.68 seconds. So we're on Earth, so 0.68 seconds. Length is what we're looking for. Whoops, geez. Let's try that one again. Okay, we're on Earth, so G is 9.81 meters per second squared. We're told the period is 0.68 seconds, and we're looking for length. Okay, so we want to do a little bit of algebra here. This is probably one of the harder formulas you're going to have to rearrange for. When we get to Doppler effect, that's a tough one as well. So we're trying to get L by itself, right? We want to get L by itself. So the first thing we have to do, or the first thing I'm going to do, is I'm going to divide both sides by 2 pi. So I get T over 2 pi equals the square root of L over G. Now, before I can go any further at all, I have to square my square root to get rid of it, which means I have to square the other side. So I get T squared over 4 pi squared equals L over G. And then I'll cross multiply. So what I actually get is I'm going to multiply both sides by G, so my G ends up there. So I have L is equal to T, which is 0.68 seconds, and that's squared, times 9.81 meters per second squared, divided by 4 pi squared. And the thing you want to be careful on your calculator here is that you put that 4 pi squared in brackets, because otherwise it'll divide by 4, then multiply everything by pi squared. And what you should get for your answer here is 0.11 meters. So please make sure you can get that as an answer before we go on to example 3. I'm going to plug right ahead, so if you guys haven't caught up at this point, please pause the video. So example 3, a future astronaut lands on a planet with an unknown acceleration due to gravity. And so it looks like that's what we're going to find. Here's acceleration due to gravity. She finds that the period of a pendulum that is 0.65 meters long, so that's the length, is 2.8 seconds. What is the value of the acceleration due to gravity on the surface of this planet? Okay, so we are now solving for g. So period is equal to 2 pi divided by L over g. And g is what we're looking for. That's what we want to solve for here. So we're gonna start this the same way. T over 2 pi is equal to the square root of L over g. So we get T squared g equals 4 pi squared L. All I've done there is I've squared, which I'm going to do here. I have to square the whole thing, and then at the same time I cross multiply. So now all I have to do to find g is divide. I have g is equal to 4 pi squared L over t squared. So 4 pi squared times L, which is 0.65 meters, divided by 2.8 seconds squared, and I get an acceleration due to gravity of 3.3 meters per second squared. Now I'd like you to get some practice here with these, with the rearranging. So at this point, I'm going to ask that you pause the video, and in your textbook, turn to page 379, and do practice problems 1, 2, and 3 on the whiteboards. And just make sure you're getting the right answer, and then if there's people in your group that are having trouble with that, see if you can help them with the algebra a little bit. Once you're finished those practice problems, then you can start up the video again and go on to the next page, which is what I'm going to do right now. So apart from talking about the period of a pendulum, we can talk about something that's called the restoring force. And the restoring force is something that's related to a law called Hooke's law. And simple harmonic motion is a special type of oscillatory motion that adheres to Hooke's law. And Hooke's law basically says that the displacement of an object is directly related to the restoring force, or related to the force causing the displacement. Now, when we actually get to talking about springs, Hooke's law has a specific formula. It says that F is equal to negative K times X, where K is the spring constant, X is the displacement, and F is the restoring force. I think on your formula sheet, it's written as, find it here, MS, yeah, spring force is equal to negative K times X. Now, we're not talking about springs yet. We're going to do springs on Wednesday. What we're talking about here is a pendulum. And in terms of a pendulum, so if we have a pendulum hanging down, that's its equilibrium position. At its equilibrium position, there's no forces acting on it. So at this point here, there's no forces. So I'm going to call it position 2. So at position 2, F net equals 0 and acceleration equals 0. If you pull that pendulum bob up, though, through some angle, we now have a force acting on it. The way that we find that force is we have a force of gravity acting down. And just like on inclined planes, what we're going to do, actually I'm going to change where I have that label, so it makes it a little easier here. So this is the force of gravity. This here is tension, and we can rewrite that tension over here. Draw it like that. And my arrows are a little smaller than they should be here. But that's basically what's going on. That's tension, and then this here is what's called the restoring force. And this angle is the same as the angle, this angle up here. So if that's position 1, I'm going to call that position 1. at position 1, the restoring force, so F restoring, you can just call it F if you want, is equal to mg sine theta, right? Because it's Fg is the opposite, Fs is the opposite, Fg is the hypotenuse, and then we know that angle, so we have opposite over adjacent, and when we rearrange that, we end up with the restoring force equal to mg sine theta. And that will also then be your net force, right? That equals your net force there, if you have to find an acceleration. So we have an acceleration that is not equal to 0 at that point. Now, the problem with this formula, one of the problems with this formula is this is not on your formula sheet. It does require some memorizing. Then just a little bit of information here. A pendulum's equilibrium position is when it's hanging straight down. At this position, the pendulum has no reason to move, and that's why there's no net force acting on it, or it doesn't move because there's no net force acting on it. Amplitude is the maximum displacement of a mass in the equilibrium position. So this would be the amplitude here. And you guys worked with that term with your lab yesterday. Maximum velocity is the speed of the mass as it passes through the equilibrium position. So down here, there's a max velocity. Although there's no acceleration, v is at a max. And for a pendulum, the restoring force is directly proportional to the displacement, right? Because that displacement is related to the tension and the angle that you're pulling it through. But that only happens when the displacement is small. So the angle has to be less than or equal to 15 degrees. Because when that pendulum has that small amplitude, that small angle, it does adhere to Hooke's law, and it is moving with simple harmonic motion. It doesn't if the angle is smaller. And you've probably noticed that if you've ever sort of been on a swing. You can swing back and forth nicely and smoothly, and you're swinging back and forth for the same period. But if you start to pump a little bit more, you get to that point where you kind of back up and you almost fall through the air. That's when you cease to then move through simple harmonic motion, and that actually happens with the pendulums, right? If you were to pull those pendulums you used yesterday up to about 80 degrees and drop it, it kind of falls. It almost goes through a free fall before it then swings back and forth nicely. So we'll just do one example here to practice this restoring force. So determine the magnitude of the restoring force for a pendulum bob of mass 150 kilograms, so 0.1500 kilograms, that has been pulled to an angle of 12.5 degrees from the vertical. So basically we have, there's our pendulum bob, and this is 12.5 degrees. And if you can memorize that formula, but you can also just draw the triangle on here, and that may help you. So this is Fg, there's the angle, and then that's the restoring force. So F restoring, Fs or Fr, doesn't really matter, is equal to mg sine theta. So that's 0.1500 kilograms times 9.81 meters per second squared times sine of 12.5 degrees. And that gives you a restoring force of 0.318. And that's all that I wanted you guys to learn today, or to do today. You can, from this now, the restoring force, you can, on page 362, there's two practice problems, numbers 1 and 2. And then in your assignment booklet, your assignment for this particular lesson, for practice, there's some text questions which involve some theory stuff. So in your text, on page 347, numbers 1 to 12 and 14. On page 380, numbers 2, 6, 9, and 10. And then in your booklet, your practice booklet, which you got yesterday, although 2 people left it behind, it was, I'm going to guess that Miranda took her, or Kate took hers, and otherwise it is Kyle and Zach G that didn't take theirs, is the guess I'm going to make. So those are up here on the demo card here, or up on the desk to the right of the smartboard. So in your booklet, it's page 3 to 4, numbers 1 to 5. So I know that seems like a lot of questions, but most of the questions in the textbook are theory questions, and you really should work on those theory ones because this is a heavy theory unit, and there will be a fair amount of theory on the exam. So thank you guys for your patience, and you have the rest of the class to work on those questions and or your lab. I will see you Wednesday.